Hi guys, welcome to this second part of this week. We are basically the week before Thanksgiving. We started the history basically of how the atom was discovered. We built so far several models, and each model basically we built was an improvement on the previous model. In a sense, it explains new experiments, or at least even new findings, or old basically suspicions that things didn't work. And then, but it also falls short of a new expectations, or at least new observations. So this is basically where we are at this point. We went from an early assumption that was made by the Greeks for the existence of the atoms to later on basically coming up with actually a little bit better, if you wish, foundations for it in early chemistry, and then chemistry and also thermodynamics. So later on, basically, the model started to appear that, hey, after the discovery of the electrons, at that point, the atoms are not charged, so there must be a positive charge out there. So the plum-pudding model was put by Thomson. Later on, it was turns out to be not correct according to Rutherford's experiments. Then Rutherford himself put basically a different picture of the atom, and that picture basically started to fall apart immediately after it was proposed, because of the fact that according to classical mechanics, at least electricity and magnetism, accelerated charged particles will radiate energy. Therefore, the atom cannot be stable. So we are at a time now that basically Mr. Bohr, I'm sorry, before Mr. Bohr, actually, there was another idea that was actually going concurrently with this one, namely the fact that the black body radiation had an interpretation based on the work of Mr. Planck, and that interpretation worked immaculately, perfectly to explain the black body radiation, but it had an assumption in it that nobody, including Planck himself, understood where it's coming from, namely that the energy levels, in this case, the light itself seems to be in a quantized fashion, in a fashion that is proportional to the frequency. Higher frequencies, short wavelengths, namely, they contribute less because of the fact that the gap between them is big, because of the fact that the frequency and the energy are proportional to one another. Low frequency, they contribute more because of the wavelength is very short, very long at that point, so the frequency is very low. So at that point, yes, they contribute more, but they have very less contribution to bigger wavelength because of the low frequencies. Remember, the energy is proportional to the frequency. The constant of proportionality at that point was fine-tuned by Planck to fit the experiments for the black body radiation, and the constant turned out to be 6.626 times 10 to the negative 34 joule second, which is the units of action, or the units also of angular momentum. It's very important to note this distinction, because down the road, Mr. Bohr will make another assumption. The photoelectric effect immediately was also explored by Einstein, borrowing the same principle, the same ideas that Mr. Planck has basically stated for the black body radiation, namely that light also appears quantized, and he basically came up with a name for those quantized versions of light, and he called them photons, which really stands for particles of light. So that's when the first time the word photon was floated. And photons also appear to be, in this case, which are particles of light, in this case, hitting the metal. In doing so, because of that collisions, they result in the ejection of electrons. So you have real particles with what appears to be waves initially, but then they are behaving like particles, meaning the light is a wave, but it's behaving like particles when you make this assumption of the photons and give them that very same properties in terms of energy and also momentum. Then you have a normal collision, the electrons ejected, and that is the photoelectric effect that you see in a lot of houses put on the roofs nowadays in the solar panels. So that explains that, and now we are at the time where we're trying to come up with a model for the atom, and here it comes Niels Bohr. So what Niels Bohr did, actually, he took the same idea that Einstein took, and he took the same idea that Planck basically proposed initially, and he applied it to the atom. Before saying that, there was another other experiments run by Compton, and those experiments basically led to also reiterate the idea of light behaving as particles, namely that extremely high energetic light, namely the gamma rays and the X-rays. Also, at that time, X-rays were not known, or even the gamma rays as being part of the electromagnetic radiation, although Maxwell's equations yield for those things. But it was until later when Mr. Röntgen actually discovered the X-rays, and it turns out to be the X-rays are part of the same idea. So the point being in here is that Compton scattering later on also reiterated the same point. So we're faced with a scenario now. That light, according to the experiments of Young, which were done in the early 1800s, is a wave, and there is no question about that. What is waving, you ask? And we saw that. It's the electric field and the magnetic field. So it's a wave with full-fledged right being a wave. Maxwell's equations that is later on were put together explain that beautifully. It has a wavelength, it has a frequency, and it has speed, namely the speed of light, 300,000 kilometers per second. So it is a wave. There is no question about it. And if you doubt it, do an experiment with a diffraction or any experiment, for example, where light hits a medium and bounces back, and you have all kinds of interference patterns that form. That proves it. There is no question about it. And and I think for those, when we did the experiment actually earlier on spectroscopy, we proved that. There is no question about it. But here are other phenomenon: the black body radiation, the photoelectric effect, Compton scattering, and now the atom suggests that light is actually a particle, namely a photon. It's made up of photons, and those particles were packets basically of energy. In this case, they're behaving exactly like particles do. They collide. In the collision, they exchange momenta, and they impart impulses to other particles and do stuff that normal particles do. So the question is, what is light? Is it a wave or is it a particle? And what is going to emerge off of this is later on in new physics called quantum mechanics. We're going to explode that idea and state that not only light can do that, not only light can have this duality, if you wish, not only light can behave as a particle and a wave in the same time, but also particles do the same trick. Electrons also can behave like waves. If you don't believe me, just look at any kind of electronic microscope that is out there. There are all kinds of applications for that. So they took the whole argument and they flipped it upside down. And now we have quantum mechanics that came way after the Niels Bohr model. So we still have to really put the Niels Bohr model first. Then once we put that, then down the road, we're going to talk a little bit about quantum mechanics. And quantum mechanics, by far, is the most precise science, period. It's not just physics, most precise science out there. And it's going to measure things, calculate things with precision that is astounding. That is, no other science can make that claim. And it's based on this argument that particles and waves, they intermingle. They actually are two sides of the same thing. Okay? So it's really a fascinating thing right now. I mean, without quantum mechanics, you would not have any cell phones, you wouldn't have any of this electronics, so that you guys know. I mean, it's really the foundation of modern technology. It's really everything that we do nowadays is built actually on the advances in this field. Okay, so let me share with you the screen to see where we stopped last time. Let me prepare it first of all, because I don't think, yeah, it's in here. So let me share. Okay, so again, we reached the point now that Mr. Basically Einstein explained the photoelectric effect using the same technique, namely the idea that light, every frequency has an energy that is proportional to that frequency. Every light that has a given frequency has this energy. Usually when we talk the word light, it's kind of loosely meaning the entire spectrum, not just the visible light that we see. When we talk literally about the regular light, it's contained between the red and the violet. There is the blue here that we see very immediately close to green. the yellow, then the orange, and there is in between them, okay, by the way, there is all kinds of transition frequencies. So in here and there, it's not like a clear cut, this transition, there is all kinds of values. The shortest wave, the longest wavelength that we can see is about 700 nanometers. The shortest wavelength that we can see is about 400 nanometers. Give and take few nanometers here and there, okay? So it's not really an exact value in here, but that's a range. So this is the visible light. There are far longer wavelengths than the red. One of them is the infrared. And that is actually light too. So when we say light, although we don't see this, but we include it as part of the spectrum. There is even longer than that, which is the microwave. And even longer than this are the radio waves. Okay. There is actually a little bit shorter than the violet, and that is the ultraviolet, less than 400 nanometers. There is even shorter than that, which are the X-rays. And even the shortest that you can even think of, they are the gamma rays. So this is basically in a nutshell where this transition between one zone and zone is really fuzzy. It's not really a clear-cut line where these things change from one side to the other. So the wavelength is increasing this way. So this is long wavelength. And on this side, it's actually what is increasing are the frequencies. This is high frequency. So this is the spectrum. So when you sometimes hear me say the word light, what I really mean is everything, not just the one that we see. As a matter of fact, I exaggerated its width in here. It's only about 300 nanometers. That's all the range between the high and the low. So very narrow. These things can be extremely short, of the order of a Fermi, which is the smallest distance you can think, or even less than that. I mean, the Fermi is the distance on the nucleus size, which is 10 to the negative 15 meters. And this is of the order of 10 to the negative 7, actually, meters. So it's about what, 100 million times longer than the Fermi. And even in here, you have the order of a kilometer. So this is of the order of 10 to the power 3, 10 to the power 3, 10 to the negative 7. That's what, 10 billion. So the range is very wide. That's the point I'm trying to say in here. What we see is actually very narrow band. That's the visible. But the light in here, when we talk about it loosely, we mean the entire spectrum. I know we had this discussion before, but because of the fact that we are using this expression now, that energy is proportional to the frequency, where h is just a constant, h is just a number, okay? That Mr. Planck basically computed to match the experiment on the black body radiation. That's all. The units for it are joule times second. F is a frequency. That means that this gamma rays are highly energetic than anything else. X-rays are highly energetic compared to the rest, with the exception of the gamma rays, which have more energy in them than the X-rays. Ultraviolet have far more energy than anything else in here because they have higher frequency than anything else, with the exception of these two, X-rays and gamma rays, and so on and so forth. So if you go down the road this way, less and less energy you're going to encounter. The least one is the one that is used for telecommunications. Radio waves is used on your cell phone, for example. Okay. And there is a reason why you would want to use radio waves in this case, because they have very long wavelengths, which means that allows them to travel far more before they start to disperse. So actually, this is the reason why you use radio waves, and you cannot use, for example, ultraviolet radiation to send a signal using for telecommunications, whether on cell phones or for TV signal or whatever you're trying to send. Okay. Anyway, so this is basically the whole range, basically, of the spectrum, and this is each and every one of them carries this energy. Okay. Note that the frequency has the units of 1 over joule, 1 over second. And this one has joule times second, so the energy is properly in the units of a joule. Okay, so the units match beautifully, because this one is joule times second divided by second, cancel the second and the second, and you will be left with the joule. So again, this is what is emerging, and we're not talking in here, at least in the book, they're not referring to Compton scattering, and Compton scattering is a very important phenomenon. Actually, it's the one that is responsible for us looking at the sun to begin with and having light coming from the sun, because inside the sun, after each basically nuclear reaction where 4 protons merge to form basically a helium nucleus, with two of the protons, I'm sorry, you have 4 protons mix to form helium, and helium that is positive in this case because there are no electrons in it. So after it emerges off of this process, there is particles called neutrinos, which are going to be covered down the road, but there is energy. This energy is in the form of gamma rays. We don't see gamma rays. Nobody can see them. They're actually a bit dark. We don't see even X-rays. We don't even see UVs. It has to be in this range. And the sun peaks looks like this. So that's, if you're asking what is the black body radiation, the sun is an example of that. This is the spectrum of the sun, where the temperature of the sun, or the surface temperature, is 5,800 Kelvin. We're not talking about the core where the nuclear reactions happen. And this is where it peaks at. So this would be your short, which means the violet. So this is the wavelength, by the way. This is where the violet is, and this is where the red is, and it peaks somewhere in between, and that's why we see the sun visible. But the rays that come with it are actually in this region, very near the beginning. They are practically 0, 10 to the negative 15 meters. 10 to the negative 15 meters, they're in this range. And they somehow started to lengthen and lengthen and lengthen and lengthen and lengthen. And by the time they emerge from the sun, they become in the visible range. So they're long enough for us to see them. So how does that happen? You're asking? Well, it's easy. So this gamma ray that emerges immediately finds an electron, hits it, and the electron bounces with an energy that is going to take from the gamma ray that just formed. So in this case, its energy is lowered because it loses some of the energy. So this is the incoming photon that is coming from this process where the helium is formed and the energy of the sun is generated. So it hits an electron. The electron moves now, that is inside the core of the sun. And now this one loses energy. So it came with an initial frequency. Now it's going to end up with less frequency. Since it's a less frequency, it's going to move in this direction. So it was here, it's going to start to move in the opposite direction, meaning that the wavelength was very short. Now it's going to start to lengthen. By the time it emerges from the sun, it's going to be in the visible region, and we can see the sun. Otherwise, we wouldn't be able to see the sun if the gamma rays come straight through to us. Okay, first of all, they're deadly. We will not be able to see anything. We'll die, okay, because they are super energetic. Remember, the energy is proportional to frequency. Thank God, actually, they are there. I remember this phenomenon is there. So, and then you're asking, oh, it did not move wholly because it's still high. Well, this one is going to encounter another electron and is going to shorten, and this one, lessen the frequency, encounter another, so it's going to bounce again. It's going to encounter another electron, bounce again, and so each time it's going to, how long does it take this one? It takes about 100,000 years before it actually emerges from the sun, before it reaches this point. So the light that you see today from the sun did not get formed from the sun today. It was formed 100,000 years ago because of this phenomenon. This is what I'm talking about. This is the Compton scattering. It's an important phenomenon, and it's all based on this relationship also. So again, we have at least 3 arguments at this point that are supporting this idea that light is a particle and it has an energy and it has momentum. So Mr. Bohr came up with the same interpretation. Remember the picture that emerged from Rutherford at this point? We have a nucleus, that is very small. This is based on experiments with gold and later other metals also. And far away, very, very far away, you have electrons. The separation is huge. Okay, the separation, this is of the order of 10 to the negative 10 to the negative 15 meters. And this one, the distance from here to here is about 10 to the negative 10 meters. And that is about 100,000 times bigger than the size of the nucleus, or the size of the nucleus is 1/100,000 that of the atom. And if you were to replace the nucleus by the sun, the Earth will be actually very close. So meaning that the atom is mainly empty. Far emptier than the solar system. In other words, if you take the Earth and put it where the electron is, and you have the sun in here, the sun would not shine as bright at all. It would completely be dark day and night because of the fact that the sun is very, 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 very far away compared to what it is today. So that's basically the whole argument in here, and that is coming from Rutherford experiment. Rutherford experiments. By shining alpha particles on a foil, or at least a sheet of gold, and he expected it to go straight through without completely not bouncing at all, because he thought that, according to Thomson's model, that the positive charge is smeared throughout the entire atom. Therefore, it's weak. So the alpha particles that have two positive charges should sail through it without completely being unimpeded. It turns out, after his students review the data, that some particles actually bounce back because they encountered a very concentrated positive charge. And he was able to find the size of that based on the angle, the minimum angle distance that you have. It's called the cross-section. Based on the cross-section, he was able to find the size of that nucleus. And this is where the numbers came in. Obviously, there was a problem with this model, as I was saying last time. According to classical mechanics, you're arguing in here, it's like the planetary system of the Earth. Again, this is where the nucleus is. This is where the proton is. So the attractive force in here that is due to electricity, which is a product of the two charges, since both of them have the same charge. The electron has E and the proton has E, so it's E squared, divided by the distance squared. This is the force that is responsible for retaining it. So if you're tempted to say this is equal to m times velocity squared over r, this is the centripetal acceleration. This is the mass of the electron that we found that it's 9.11 times 10 to the negative 31 kilogram. Okay, so if you're tempted to do this reasoning, there's a flaw with it big time, and namely the fact that since it's an electron is a negative charge, doesn't matter, it's a charged particle that is in motion and it has an acceleration. Since it has an acceleration, it should lose energy. In doing so, it's going to spiral down and fall on the nucleus. So the atom is not stable. So that was the biggest problem with this whole thing. Now, Bohr proposed the following. He said, allow me the following assumption, okay? That while the electron is true orbiting the nucleus, its angular momentum is fixed. It doesn't change. So basically he said, okay, this is where the nucleus you said is. And this is where the electron is. It's going to orbit this electron so that its angular momentum must be fixed. And in order for him to fix the experiment so the data match the spectroscopy, he had made it into a fixed number where n is an integer, being 1 or 2 or 3 or 4 or 5 and so on and so forth. So all the integers are possible, not 0, of course. 0 is not allowed. Times the constant of Planck that Mr. Planck has found again, so it's made its appearance again in here, divided by 2 pi. That's it. That is the first assumption. Meaning that actually it's really a wave whose wavelength is an integer multiple. It's going to turn out to be of this path. That's it. So the first assumption is that the angular momentum of the electron, this model, by the way, works for the hydrogen only, because he tried to make it work for other atoms. It did not work for him. So if you look at the periodic table, it works for this model, for this atom, I'm sorry, for the hydrogen only. Okay, no other element in the periodic table. I mean, you can try to make it work for helium and the rest of the elements in the periodic table, but it doesn't work, okay? It doesn't work. Anyway, so you're asking, okay, how about the rest of the elements in the periodic table? Well, we're going to come back later into it. We're going to try to explain them with other models, basically, with quantum mechanics, really. That's when it's coming to save the day. Because up to this point, even this H in here has no explanation. We really have no idea where these things are coming from. The whole business started with Mr. Planck trying to explain this phenomenon, the blackbody radiation. Then later on, Einstein borrowed it to explain something else, and Compton borrowed to explain this. So the same thing. Now it's the turn of Mr. Bohr trying to explain the atom. That's all. So it's still kind of mysterious how it came about at this point. Okay. So angular momentum of the electron is an integer, a positive integer, multiple of Planck's constant divided by 2 pi. Actually, sometimes this Planck's constant divided by 2 pi is also called Planck's constant. So H divided by 2 pi. Remember, H is 6.626 times 10 to the negative 34. Divided by 2 pi, 2 pi is roughly 6.28. So if you do the division, you're going to find that this number is 0.55 times 10 to the negative 34 joule second. So it has the same units because all you're doing is dividing it by a number, that's all. So it's the same units. So in the literature, actually, and this is you might encounter it, you'll find it as written as H also, but with a cross across it. That's it. So if you're reading through this and you're trying to see it, you might see the symbol, which is the same H, except has a line across the long bar of the H. This is, you read it as H bar. So the same constant divided by 2 pi is also a constant. Of course, it's a fixed number, it doesn't change. Pi is constant, 2 is constant, H is constant. So everybody is constant, why not this one is constant? This one in the literature sometimes is referred to as Planck's constant too. So both of them are Planck's constant. And honestly, in science, this one has more value in it because it appears far more often than the H itself, okay? So you can say that it's Planck's constant divided by 2 pi, meaning what you mean by the Planck's constant, 6.626, 10 to the negative 44. That's what you mean. Or the entire thing as being Planck's constant, because all you're doing is that taking that number, dividing it by 2 pi, and you're going to end up with another fixed number that doesn't change. So the angular momentum, which is the symbol for it is L, is just an integer n times this number, times 1.055 times 10 to the negative 34, okay? always fixed. So the lowest value that you can have, the least value that an electron can have, least value is going to be h over 2 pi. Obviously, if the angular momentum is 0, this electron will stop from moving. And if it's not moving, there is no reason for it to stay there, so it's going to fall. So the only reason for it to stay in orbit is that if the angular momentum is not 0. That's why n cannot be 0. So n has to be more than 0. That's why I said it's a positive integer, always bigger than 1. And the reason why it's positive is because we're talking about the magnitude. So we don't care if the electron is spinning this way, positive direction, or the electron is spinning this way in the negative direction. So what we're talking about in here is the magnitude. We don't care about which way it's spinning, okay? Obviously, the whole configuration is in 3D, so it could be moving every which way. So the sign is irrelevant at this point. What is important is that the magnitude, how much rotation it's going to have in order to go around the nucleus. So, and since it's a magnitude, it's always positive, and I mean, it can be 0, but it cannot be 0 in this case, because if it's 0, that means it's not moving at all. And if it's not moving, there is no reason for it to stay in orbit. It's going to fall immediately. So then we have a problem, okay? So that is what the angular momentum is, okay? In classical mechanics, and I know we didn't cover this chapter in detail, the angular momentum for a point particle is the mass of the particle times its velocity times its radius, because it's going to spin somewhere. So if this is the nucleus, this is what I mean by the radius, okay? So it's a particle that is spinning with a mass m, and it has a velocity v. So you take the mass velocity times how far it's spinning from the center of rotation. In this case, it's the nucleus, times the radius of rotation. So this is the angular momentum. So the picture now that emerges is that the angular momentum is an n number fixed times h over 2 pi. I'm going to write it n h bar. It's the same thing, okay? It's just h over 2 pi is easier to write it as just one thing. H, and then have a cross around it. That's all. So this is the first assumption. Of course, there are two other assumptions. The first one is that while orbiting, because he needed to understand how come the atom is stable. While orbiting in its fixed radius, he made the assumption that the electron does not emit or transmit. It's stable, okay? The atom is stable, basically. Stable or when an electron is in the same orbit. I'm going to put the word orbit in here, but we're going to talk about energy levels, and you will see that it has immediate connection with the energy levels. The third assumption is in here. The atom emits light, emits or absorbs if an electron transitions either down, in this case it's going to emit, or up in its orbit. Meaning, if n does not change, remember delta n is a change. There is no emission. The atom is stable. So now we're looking at this picture. There is an atom. The electron can be here for n equals to 1, or here for n equals to 2, and so on and so forth, or n equals to 3, or so on and so forth. If n does not change, meaning it stays at n equals to 1, or it stays at n equals to 3, it doesn't matter. Then in that case, there is no light that is emitted or absorbed. Now, if it transitions from a higher level to a lower level from N2 to, in this case, it's going to emit light. If it transitions backward from lower to higher, then in this case, it needs to absorb light. So this is an absorption, and this is an emission. Okay, so that is basically in a nutshell what's going on in this case. So those are the three assumptions. Let's see if they work, because later on they will work immaculately for the hydrogen atom. Then they don't really work that great for helium and the rest of the atoms. I mean, they will work for helium under one condition: if you take one of the electrons of the helium and make it ionized, so that the helium at the end will have 2 protons in the nucleus and 1 electron. Then it's going to work. So what I said earlier about the fact that the model that Mr. Bohr came up with does not work for all of the other elements with the exception of hydrogen is not exactly 100% true. It works for anything in the periodic table, if you wish, as long as you strip them from their electrons completely with the exception of 1. Then it's going to work. But that's not good enough, of course. We need to understand why that is. So we're going on with the rest of the stuff in here. So, okay, we're going to do a little bit of calculations in here because I think I saw it in your book. So it's not the calculation I gave you a result, but I don't remember the result. So I'm going to give you how that works, okay? So again, the angular momentum is a fixed number. That's what we just concluded. Then we know also F equals to ma, namely the fact that the one that I wrote earlier, the force between an electron, this is a constant. This is just 9 times 10 to the power 9. This is a constant. This is Coulomb's law, by the way, of the charge of the electron times the charge of a proton. And in this case, for the hydrogen atom, they're the same. So I have a proton that has a charge positive E, an electron that has a charge that is negative E. So in magnitude, both of them are E. So Q is equal to E for the electron in magnitude, and Q is equal to E for the proton in magnitude. Okay, and the negative sign means that just they're attracting each other, that's all. And we need it to be attracting. I mean, we don't want it to be repulsing, because if it is a repulsive force, then it's going to not be stable at all. So that's not going to work. So divided by the distance between them, and the distance is r squared. So this is Coulomb's law. Constant times the product of the 2 charge divided by the distance squared. This equals to the mass of the electron times the velocity squared of the electron divided by r. So again, this is the centripetal acceleration. This is the mass of the electron. The centripetal acceleration, which is v squared over r, times the mass, is equal to the force. That's in a nutshell. So this negative sign, if you're worried about it, it's on both sides, so it cancels. So I'm not going to write it down. Well, let's rearrange this expression a little. So I'm going to move the r squared on this side, and I'm going to move the m on the other side. So what this expression looks like is r squared times v squared over r is equal to this constant ke, which is 9 times 10 to the power 9, a Newton per Coulomb squared times meter squared. Okay, so the units for it. So it's going to be Newton meter squared over Coulomb squared if you're worried about the units. Times the product of the 2 charges, which is E squared, divided by the mass. Remember, I moved the mass, so it's going to go downstairs, the mass of the electron. Obviously, r squared and r cancel, and I'm left with these 2 expressions, which I'm going to write them on top of one another. So on one side, I have r times v squared. Remember, one of these r's is canceled with the other r, is equal to this constant ke times e squared divided by m. And on the other side, I'm going to write the same expression in here. I have v times r. I'm going to divide the first expression by m. So this expression, I'm dividing it by m. So it's going to be just this constant n times h bar divided by the mass of the electron. I have 2 equations. I don't know what r is. That's the whole reason why I'm trying. I don't know what the velocity is either. So I'm going to solve this 2 by dividing those 2 equations side by side. When I do the divisions side by side, the r and the r cancel. So this, I'm sorry. The r and the r cancel, and the v squared and the v cancel. So I'm left with a v in here. And I am left with also the m and the m cancel too when I do the divisions. because 1 over m divided by 1 over m is just 1. So I'm going to be left with Ke times E squared divided by n times h bar. So this is how fast the electron moves. So this is its velocity. Okay. Where n is that same integer. So the higher up in the orbit, the slower the electron is going to appear. That's what this expression looks like, because as n increases, this velocity becomes less and less. This is not really an important quantity for us at all. As a matter of fact, you will see later on in quantum mechanics that this doesn't make sense at all. But it's a good number, trying to see how fast the electrons are moving around the nucleus. That's all. Now, this is one thing. So I have the velocity in here. I need, honestly, to find this R. That is more important. We want to find how far the electron is from it. In other words, we want to know how big the atom is, okay, for the lowest value of n, which is 1. So that is really immediate consequence of this whole thing. So we found V. We take any of these expressions, whether R times V equal to NH bar over M, and then find from it what R is. So remember, we have V times R is equal to N times H bar divided by M. I just found what V is. So I'm going to replace it, but I can divide by it first to find what R is. So R is N times H bar divided by MV. Let's replace this V in here that we get from here into this expression. So it's going to be N times H bar divided by the mass and divided by the velocity. And the velocity is this whole thing, which is Ke times E squared. And then when I divide by NH bar, I have to multiply by NH bar in here. So here is the picture then. The radius seems to be dependent on this integer n, and that's why the book, they put the index n in it, because it depends on n, and it's equal to n squared times this h bar times h bar, that's h bar squared, divided by the mass of the electron times this constant, which is the same number that I wrote earlier, 9 times 10 to the power 9, and that divided by e squared. Okay. This whole thing is just one number. This whole thing is just one number, which I'm going to write it as A naught. The book writes it as a R1. You can write it as R1 if you want to, but every textbook writes it as N naught. So the book writes it as R1, okay, is equal to M squared times Rn. So this number A naught is, for n equals to 1, that is actually true. 1 squared is equal to R1. So this is the smallest size that we're going to have, the closest the electron will get from the nucleus. If you plug in the numbers, basically this A naught will be simply H bar, which is 1.055 squared, times 10 to the negative 34 squared, that's 10 to the negative 68, because 34 plus 34 is 68, divided by the mass of the electron. The mass of the electron is 9.11 times 10 to the negative 31, times this Ke, I just wrote his value, which is 10 to the negative, I'm sorry, which is 9 times 10 to the negative, 10 to the positive 9, that is, times E squared. E squared is a very small number, which is, I'm going to write it as 1.6 squared times 10 to the negative 19 squared, which is negative 38. Okay, I have a bunch of numbers in here. The first thing usually that you need to do is the powers. 31 minus 9, that is 22. So it's 10 to the negative 22 and 10 to the negative 38, that's 10 to the negative 60. So this is how this number look like then. It's 1.055 squared divided by, first of all, I have 10 to the negative 68 in here and divided by 10 to the negative 60. So you're asking, where did I get the 60? I have negative 31 plus 9 minus 38. If you do the calculations, you will find that 8 plus 1 is 9, and then that cancels the 9. You will have will be left with 6 plus 6, which is 3 plus 3, which is 60. So it's a negative 60. So that's what the denominator is, and then at least in terms of the powers. And then you have the other numbers. You have 9 in here, you have 1.6 squared, and you have 9.11. So again, it's 9.11 times, that's coming from the mass of the electron, times 9. 9 is coming from that constant, I'm sorry, a lot of you complain, especially those on the lab, about my nines similar to the G's. There are no G's in here, it's all nines, okay? Times 1.6 squared. And if you do the calculations, first of all, this is 10 to the negative 8. So in here, 60 and 68, you'll be left with a negative 8 in here. But you have in here a 9 and a 9, which is about 81, times 1.6 squared, which makes it about 100. So you're going to end up with a number that is very, very small, as a matter of fact, in this case. And the whole answer is going to be, if you plug in the numbers, is going to be 5.3. So there will be a 10 to the negative 3 in here, plus 10 to the negative 8. That's going to be 10 to the negative 11 meters. Wow. Remember, 10 to the negative 10 is an angstrom. That's what the 10 to the negative 10 is. So this is actually about half an angstrom. That's the size of the atom. Any other level is this many squares. So that means the first level is at a distance of this much. The next level is, for n equals to 2, is 4 times, because it's 2 squared times this number. So it's 4 times this number. The next level, which is 3, which is going to be 3 times 3, that's 3 squared. Remember, the formula has an n squared in it. So it's going to be 9 times this number. And so on and so forth. So that's the size of the atom. And it's a very important concept in here. So that's actually part of your lecture stuff too. You don't need to remember how we got this number. The only real thing that you need to remember is the radii for a given energy level n is proportional to the square of this integer times this number that does not change, which is about 5.3 times 10 to the negative 11 meters. That's all we need to remember here. So that's what A naught is. Okay. Another quantity that is of interest to us is actually the energy. And the energy comes from 2 contributions for the electron. The energy of the electron is the sum of the kinetic energy plus the potential energy. And we saw this a long time ago. The kinetic energy is 1/2 mass times velocity squared. And the potential energy, in this case, it's negative. The reason why it's negative is because of the fact that you have 2 different charges, positive and negative. So it's Ke times the product of the 2 charges, which are the same, E squared, divided by the distance, okay? So now take any of the expressions that we have found for R and V, and you're going to find the value that is going to be equal to a constant. Energy is going to be equal to a constant, which I'm going to write down in this case, negative 13.6 electron volt divided by n squared. Okay, let me emphasize where these numbers are coming from. Remember V, we just found what V is. V is Ke times E squared over NH bar. So the velocity in here, V, is equal to I can't memorize these things. It's Ke times E squared, constant Ke, times E squared divided by NH bar. So that's what the velocity is. So you're going to multiply it by 1/2 and the mass, and you're going to square this number. So it will be Ke squared times E to the power 4 divided by N squared. That's where the N squared comes from, times H bar squared. So this is one thing. This is going to be exactly the same quantity, except it's going to be twice as much, because Ke and E squared divided by R. And R, we just found what R is. Actually, you can replace this whole thing. R is going to be dependent on N squared. So it too will have an N squared in the denominator, hence where the N squared is. And times H bar and MEKE squared. So this will go upstairs. And remember, you have an E squared already. So it's going to square the square, which will give you the E to the power 4. So if you combine all of this, it's going to be a number, but it's going to be in joules. So you'll have in the numerator E to the power 4 everywhere, times constants in here. Actually, I can write it down too, honestly. It's not that hard, really. So it's going to be negative M times Ke squared divided by Ke divided by 2 times N squared H bar squared. So that's the final expression. This is when you combine both 2 terms. It's going to be a negative answer because this one is twice as big as that one. That's all. Okay. And it's important why the number is negative. You want it to be negative because you would want the total energy to be negative so that it's bound to the electron, the proton. You don't want it to be positive, otherwise it will have enough energy to escape. You don't want the electron to escape for a normal atom. You want it to stay where it is. So now, if you plug in all of these numbers, you find the answer in joules. KE is 10 to the power 9 times 10 to the power 9. When you square, it's going to be 81 times 10 to the power 18. The mass of the electron is 9.11 times 10 to the negative 31. This one is 1.6 times 10 to the negative 19. When you square it, it's going to be 1.6 squared times 10 to the negative 38. When you square the square again, it's going to be 1.6 squared times 10 to the negative 76. Divided by n squared, which is, you don't change it. So this energy now depends on n2, okay? And then you have an h bar squared, which is 1.055 squared times 10 to the negative 68. The answer is going to be in joules. We usually don't write it in joules because the number will be too tiny. So we write it, we drop one of this e to the power 4, and we write it e to the power 3. So don't multiply by the cube, by the square of the square, but rather by the cube of this number, which is negative 57, which is 1.6 cubed times 10 to the negative 57. If you do this calculation, the answer is not going to be in joules, but rather in electron volts. So this is the electron volt. And this is a famous result, by the way. This is a well-known result. 13.6 is a well-known result for the hydrogen. This represents the ionization energy of the hydrogen. When you take an electron from its lowest level, which is n equals to 1 to infinity, basically far away. When you put infinity, that you divide by infinity, it's 0. So that's what the answer is coming from. So this is the picture that emerged then. The lowest energy level for n equals to 1 is E1 equals to negative 13.6 electron volt. For n equals to 2, E2 is going to be negative 13.6 divided by 4, because 2 squared is 4 electron volts. And this is 13.6 divided by 4, it's slightly more than 3 point something electron volts. Get the calculator in here quickly. I don't memorize this number, by the way. I know they are in the book. 13.6 divided by 4. 3.4. So this is negative 3.4 electron volts. For n equals to 3, E3 is negative 13.6 divided by 9 electron volts. It's going to be slightly over 1. So 13.6 divided by 9, and the answer is 1.51 electron volts. It's a negative number too, and you want it negative so that the electron remains intact, even at this level. Isn't it a very high level of 3? N equals to 4. E4 is going to be negative 13.6 divided by 16, because remember, 4 squared is 16. So it's going to be less than 1 now, electron volts. So 13.6 divided by 16, and the answer is 0.85. Negative 0.85, negative 0.85 electron volts, okay? N equals to 5, and probably we're going to stop in here. N equals to 5, E5 is equal to negative 13.6 divided by 25, because 5 squared is 25, okay? It's never going to be 0, by the way, no matter what you do. Divided by 25 is 0.54, 0.544. Why is the electron volt? So even if you put 10 in here, so we're going to go all the way to n equals to 10. So it's going to be E10. It's still negative 13.6 divided by 100, because 10 times 10 is 100. And this is going to be negative 0.136 electron volts. So it's never going to be 0 actually, okay? Even if you go all the way to 10 in this case. Even if you go to 1,000, still negative number. So here is how the picture looked like then. The lowest energy level is negative 13.6. Remember, negative numbers are smaller as the number becomes bigger. The second level is at negative 3.4 electron volt. The next level is midway, which is about negative 1.5. And the next one is about halfway, which is 0.85 negative also. The next one is slightly closer, and the next one is closer, and so on and so forth. Okay, so now that explains everything. If you want to go from n equals to 2 to n equals to 1, you're going to emit light, so the electron transition, and it's going to emit light that corresponds to the gap. So negative 13.6, we subtract it from negative 3.4, and it's going to be a positive number, by the way. So it's going to be a positive 10 point something. Hold on. Or is it going to be less? Hold on. Yeah, negative. Let me write it. Oh man, I don't mean to subtract this number. So let me start. Okay, so let me start again. I'm going to take these numbers. It's going to be 10.2. But it's going to be a positive number. So it's going to be a positive 10.2 electron volts. Remember, the energy is equal to H bar, HF. So the energy, in this case, if you want to have it in joules, again, you're going to convert this one back to joules by multiplying by 1.610 to the negative 19. And you're going to have a frequency. So if you're curious how much frequency is emitted in this transition, all you have to do is take 10.2 times 1.6, 10 to the negative 19, and divide by that by 6.626 times 10 to the negative 34, and you're going to find how much frequency you're going to have. End of the story. The opposite is true. If you would want to go from here to here, you have to supply energy, and that energy is going to correspond to this gap of energy. So in other words, you have to supply frequency. So that's an absorption spectrum. This is an emission spectrum. So everything fits beautifully. And this explains the Lyman lines, basically, that correspond to transition to the n equals to 2 level. So people saw for hydrogen, for example, that it has specific lines in their emissions. You have 4 lines called the Lyman lines, that because Lyman is the one who discovered, he basically studied them and discovered them, and therefore, was it Balmer? Anyway, Lyman actually is at higher frequencies. So in this case, if you study them, you will find that the transition corresponds to certain frequencies that are proportional 1 over n squared, and this fits beautifully. And this is the transition to the n equals to 2 level in the visible. N equals to 2. Because transitions to n equals to 1 have higher energy that we don't see. They're actually in the X-ray that were discovered by Mr. Rangan toward the end. I mean, after that. So n equals to 1, transition to n equals to 1, is higher energy. They happen to be in the X-ray. We don't see them. In the visible range is n equals to 2, and this is visible. These are the spectral lines for hydrogen. So the theory fits beautiful and explains spectrum for hydrogen beautifully. There's no question about it. There are other lines also that involve n equals to 3, n equals to 4, so on and so forth, that later on were discovered. And they're all fit under Mr. Bohr's model beautifully. But as I was saying in the beginning, this is actually has a shortcoming in a sense that it does not explain, for example, the helium atom, at least the stable, the neutral helium atom. It explains only up to basically the ionized version of it, or any other element that is fully ionized with the exception of 1 electron. So later on, we're going to discuss the new theory that explains all of this and beyond, and that will give us an interpretation of the periodic table And the periodic table would really be explained by the energy levels that are n equals to 1, 2, and 3, and 4, and so forth that we have, but there are actually subdivisions to them. They are related actually to the angular momentum and to the spin of the electron. Combined all of this, each energy level has a subdivisions depending on the angular momentum and the spin, and that is how the electrons are distributed in a periodic table. And if you take any periodic table, like for example, the one I have on the back in here, it has the energy levels actually represented in here with this SPDF representations in here. And that explains the periodic table that Mr. Mendeleev put together, and everything now fits, at least the chemistry of all the elements fits beautifully in this pattern. Okay, again, this is not in lieu of reading the chapter. You must read it, you must go through it, you must understand what's going on in there. Come back to this video, hopefully, for an explanation of what's going on. And if you have any questions, please reach out. And we already have an assignment that we discussed on Monday from this chapter. So we had it in the lab. So for those who missed the lab, and there are a few who missed the lab, please reach out, because you're going to be accountable for these materials when come exam time. Namely, you will have two sections again in the exam, one that is conceptual and one that is actually problem solving, the part of it. So we discussed in the lab on Monday several chapters dealing with electricity, basically electrostatics, namely Coulomb's law that we mentioned already today several times, a chapter dealing with electronic circuits, basically, and that's an important one because that's mainly with Ohm's law, so it's an important topic in there. And then we had another chapter also that we covered, has to do with the magnetism and the electromagnetic force, and we had that also in the discussion on Monday. And we also discussed problems from this session that focused mainly on Planck's law, E equals to H times frequency. So all of this was done on Monday, and it was done live in person on campus. So if you have any questions, please reach out to me. I already posted the problems that we have in there on Canvas. So look at them again, make sure you understand them. If you have any questions, please reach out to me. Happy Thanksgiving, and I will see you guys on Monday, November 28th, the week after Thanksgiving. Thank you.